Everyone, this is Hardik from fuzzing.in. Thank you for watching my videos. In our last videos, we have seen different fuzzers like AFL, AFLplusplus, libfuzzer, hongfuzz, and very recently we have seen libafl. We've been using a simple program, that is damn vulnerable C program, to understand various fuzzing concepts. Now what we are going to do in this video is that we are going to add some checks so that it becomes a bit harder to find the input, and then we will see how does our fuzzer works and then what we can do for that. So we are going to see the concept of CmpLog, that is CmpLog, CmpLog, and we will see how it can be utilized to generate complex input or to fuzz the complex program where they uses some comparison operations. Like if you want to fuzz some image file, then you might be aware that they expect certain kind of header. So if we don't provide that header, then our program will simply quit and it won't proceed further. So we won't find any crashes if we don't use proper header. So there are different approaches, like we can use dictionary, and there is another approach. If we don't want to use dictionary, we can use CmpLog feature. So in this video, we are going to see what is CmpLog and how does it helps, and how can we compile our program with CmpLog feature using AFLplusplus, and then we will see how can we fuzz that using AFLplusplus. So let's start. So let me open our imgRead.c program. This is the program which we have been fuzzing in all our videos with various fuzzers. So let us see what we can do to make it harder to fuzz. I hope that you are comfortable with this program now, and if you are not comfortable with this program, then I will recommend you to go to my channel and look for the older videos that will give you a generic idea of what this program is and how does it work. So let us go ahead and see. I will explain this program in short. So there is a main function which calls a function that is called process image with the provided argument, that is a file name. And if we go to this process image function, you can see that it basically opens this file, it performs some sanity checks, and then it uses one while loop where it keep reading the data inside the structure. That structure is img structure, and it has been declared over here. So this structure has one header which is of 4 bytes, one width, height, and then some data over there. And then it performs various operations, like it will add image width and image height, then it will allocate some memory based on that, and then we try to copy some data to that newly allocated memory. So it contains a lot of vulnerabilities like integer overflow, heap buffer overflow, and all kind of vulnerabilities. Previous videos, what we have done is that we are simply trusting the data which it was reading from the file. So in this case, it was reading the data in the structure, and we are not doing any sanity checks whether image.header contains img or not. We are not doing any header check over here. We are simply processing the data over here. You can see that there is a printf statement over here which was simply printing header, width, height, and data. So this keep check has been commented out. This is actually a string compare which actually compares the image header with the tag that is img. So there, if we remove this comment, what will happen is that it will actually checks inside the while loop. Whenever it enters into the while loop, whenever it reads the data, it will actually verify that image.header actually contains img. If it contains, then only it will does the further processing. Otherwise it will not do any processing. It will simply display a message that is invalid header, and then it will quit. So we will not find any crash if the starting 3 bytes are not img in our input. So this is a check I have enabled right now, and what we are going to see is that we will try to fuzz this. We will compile this first with the AFLplusplus, and then we will see if we get any crash, or we will wait for few minutes, few seconds, and we'll see how much time it takes to find a crash. If you recall, or if you go to the previous video, you will see that when this check was not here, the string compare where we are not verifying if img.header contains img or not. We generally used to instantly get some crash within few seconds. We used to get a lot of crashes. So let us go ahead and see what happens if we simply verify this header value over here. So this is the command to compile our program. We are using afl-clang-fast over here. Then our input file name, that is imgRead.c, then -f-sanitize is equal to address and undefined. It means that we are enabling address sanitizer as well as undefined behavior sanitizer, and -o, and then our output file name. So I have intentionally named my output file name as imgRead_afl++ over here. And then when we'll use CmpLog feature, we will append CmpLog in the file name over here. Like it will be something like imgRead_CmpLog. So let us compile this, and you can see that we have compiled this. And now what we are going to do is that we will create one input corpus. So I'm simply using 3 bytes, that is xxx, and I have created one folder, that is in CmpLog, and then 1.img. So this is the file, and we can actually check the content of this file. So you can notice that this file, this input file 1.img, it simply contains 3 bytes, that is 78, 78, 78 in hex, which means that in ASCII it is xxx. Now I have intentionally given xxx instead of img because we want to test the CmpLog feature. So now if our fuzzer is really efficient, then it should locate that our executable file actually expects an input which start with img and not with xxx. So let us go ahead and fuzz this program. So we will use this command, that is afl-fuzz -i in CmpLog -o, that is out, -m is none because we have enabled address sanitizer, so it will require a lot of memory. So that's why we are using memory limit is none, that's no memory limit, -- our executable file, that is imgRead_afl++. And now let's run it. So we need to wait, and if you recall previously when we did not have this check of header where we are verifying the header contains img or not, we immediately used to get some crashes, but here you can see that so far we have not found any crash. So let us wait for few more minutes and let's see if our fuzzer is able to find any crash or not. And you can also see that we are getting a good speed. We are getting somewhere around 1300 executions per second, and total execution are somewhere around like 50k now. So let us wait for a few more seconds. I think we can wait for like 4 or 5 minutes. I'm going to stop this video and I will start it again. So let's wait. So you can see that it has been already like 2 minutes and 20 seconds, and so far our fuzzer has not found a single crash yet. So it means that because of that check, our fuzzer is not able to generate the proper input and it will take a lot of time. So we need to wait, and let's wait for a few more minutes and then we will see how does CmpLog help in this case. Okay, so you can see that it is almost 5 minutes now and our fuzzer is not able to find any single crash over here. So it means that that check is actually working and our fuzzer is not able to generate any single input which can satisfy that condition. So it is basically not able to go inside that while loop, inside that if condition, and it is simply exiting. So we will face the situation very often in various software. So you can see that it is almost 6 minutes now and so far our fuzzer has not found any single crash over here. As you can see, saved crashes are 0 and total execution are around 500k. So even after this many execution, our fuzzer is not able to find any single crash. It means that our fuzzer is not able to generate an input which actually contains img, this 3 bytes at the start. It is not able to locate that thing right now, and it may take some more time, or maybe it may take a lot of time to figure that out, and we need to wait for a few hours maybe. So if we want to speed up this thing, then what we can do is that we can use CmpLog feature. So now let us go ahead and see how does this compile binary look in the IDE first, and Then we will see after enabling CmpLog how does this binary looks in the IDE. So I'm going to cancel this now, and let us open IDE and see this binary. So I have already opened this binary in the IDE, and you can see that inside this process image function, when we go, you can notice that there is a fopen call over here, and then there is afread call over here, and then you can see it over here that is comparing. There is a compare instruction over here. This instruction is important. So the CmpLog feature, what it will do is that it will basically work on this compare instruction. We will see it going forward. So you will notice that it is comparing img with this register value, basically the value at this memory location, right, R15. So if that value matches, then it will jump to this location, which is where it will print the header, width, height. It will perform all the normal operation. But if this value doesn't matches with img, then what it will do is that it will print the string that is invalid header, and it will simply exits. This is how does it looks if we don't use CmpLog feature. And in our case right now, what is happening is that our fuzz is generating some input and it is failing over at this particular location in the binary. In this case, our binary is simply printing this invalid header and it is exiting. So now to overcome this situation, we need to use CmpLog. So as you can see from AFLplusplus documentation, it has this feature where it can basically instrument all the compare instruction and it can generate dictionary based on that. So that will actually help us, and that will help us to overcome this problem which we have been facing. So what it can do is that it will basically add some instrumentation code in your binary if you enable this CmpLog feature. So the instruction are given over here. How can you generate or how can you compile your binary with CmpLog support? And you actually need to use afl-clang-fast, and then you actually need to generate two binaries. The first one is a normal binary with AFLplusplus instrumentation, and you need to generate another binary which is compiled using CmpLog support. So AFL will use two binaries in this case. And to generate the CmpLog binary, what you can do is that you need to set up one environment variable, or you can simply use this export afl_llvm_CmpLog is equal to 1, and then you can use afl-clang-fast compiler. Then you can simply compile your program with that. And to compile the normal binary, you don't need to use this variable. You can simply unset that if it is set, and you can simply use afl-clang-fast and you can compile that. And now you need to specify the CmpLog binary using -c command. So what AFL will do is that it will run both the binaries and it will use this CmpLog binary to get all the tokens, and based on that it will generate some new input, and that it will feed it to the AFL compiled binary. So in that way it will actually speed up your input generation speed. It will basically generate proper inputs which has the proper tokens. So now also one more thing you need to notice is that if you are using CmpLog, then you need to specify memory limit as none, because CmpLog will require a lot of memory as well, like async. So in case of async also we are using this option for 64 bits binaries. So we will use -m is equal to none. So now before we compile our program, let us go ahead and see the source code of AFLplusplus to get a general overview how does it works, and then we will compile our binary and then we will fuzz that. So you can see that inside AFLplusplus source code is the instrumentation directory, and which actually contains all the instrumentation related code. And here you can see couple of files related to CmpLog. So like there is one file that is CmpLog-instruction-pass. There's CmpLog routines-pass. There is CmpLog switches-pass. All these files are basically LLVM pass, which has been used by AFL, and it will add some instrumentation code to your binary. And as you can see it over here, having one function or method you can say, which is hook instructions, and there is a module, and then there is a call to get or insert function. So basically what it will do is that it will insert this callback hook over there in your binary. We'll see how does it look like in the compiled binary, and then this will be used by AFL. Like if you remember how does AFL work, it basically uses a function. It will basically, whenever it instruments the source code, it will add a callback function, that is AFL, maybe log and others, so that it will use at the runtime to trace the basic log execution. Similarly, in this case, it will add this CmpLog hooks over there so that it can trace out all the compare instruction inside your binary at the runtime, and this data it will pass to the AFL, which will use it to generate some new input. So these are basically AFL specific pass, and these are LLVM pass. It's not very complex, you can say. There is a CmpLog map as well, as you can see it over here. Like in case of AFL, we used to have a coverage map, so they will use a AFL compare map as well, which will track all the compare instruction. And we don't need to go into much detail. I just wanted to give you an idea where it is actually implemented and how does it look like, so that when you use it, you are comfortable with this. So these are the files which are responsible for CmpLog instruction. We don't need to go into much details over here. This is not required. So now let us go ahead and compile our damn vulnerable co.imgRead.c program with the CmpLog feature, and then we will see how does it look like in the IDE code. So this is the command. We need to actually use one variable, that is AFL LLVM CmpLog is equal to 1. We'll tell our compiler that we want to use CmpLog feature, and then we will use afl-clang-fast compiler wrapper over here, then imgRead.c. So remember that this file has this img check. We are verifying the actual header over here, if it contains img or not, and that is why we are using CmpLog feature over here. Then -f sanitize is equal to address undefined, then -o, and here the executable file name I am giving as imgRead_CmpLog. So now let us see what is the difference in output. So you can see that it is giving a message that is CmpLog mode by Andrea URL, and then running CmpLog switches pass. There is hooking one switch instruction, so it has found some compare instruction in our binary, and there is CmpLog instruction pass, CmpLog routine pass. So all these are from the 3 files which we have seen just now. And now if we want to see how does it looks like in IDE, so let us go ahead and see. I am using IDE freeware over here, and if you see it over here inside the process image function, when it is displaying the invalid header, if we see above that, there is a CmpLog instruction hook 4 over here, and then there is a AFL compare map. So as I have mentioned a few seconds before, like these are the instrumented binary with CmpLog, and it will have this CmpLog map, and AFL will use this at the runtime, and there is a CmpLog instruction hook, and here you can see that there is a compare instruction. And what this instruction is doing, if you recall the source code, it is comparing the image header with img. So if it is equal to img, then it will actually go to the next level, it will perform all the operation. But if it is not equal to img, then it will print invalid header and it will simply exit. So here you can see a lot of compare log related instruction hooks over here. Just before the compare instruction, there is one call to compare log. There is a compare map over here. And while if you open our normal binary, which is not compiled with CmpLog, as you can see it over here, there is no such instrumentation code. You can see, right? This is the normal binary, and this is the CmpLog binary. So you can notice the difference over here. And if you see the source code as well, there are a lot of CmpLog map and compare log instruction hooks over here. While in the normal binary, if we see the source code, we don't see any such compare instruction or any such CmpLog related instruction over here. So in case of CmpLog binary, if we just look for our invalid header string, here it is. If there's a compare map and there's an instruction hook, and if you see these bytes, These are basically img. If you convert it to character, it is img, as you can see it over here, right? And here also. So this is the chat. This is the chat in our program, which actually verifies that the header contains, this is the header, v12 is actually the header which is read from the file here. So this is how it looks like, and you compare the binary instrumented with CmpLog with a binary instrumented without CmpLog. This is the difference. You can see that there is no CmpLog related stuff over here. So this is how it looks like. And now what we can do is that we can simply run our program, and we will see how much time it takes now to actually find a crash, and if it is helpful at all or not. If you recall, we just fuzz our binary without CmpLog, and we, I think, ran it for like 7 minutes, as you can see it over here, and the total executions were like 600k, and our fuzzer was not able to find any single crash over here. Now let us see how does it changes with the CmpLog feature. So let us run our binary. The command is straightforward. We simply need to give So let me explain you the command. The command is afl-fuzz-i, which is your input directory, which contains the seed corpus, -o, which contains your output. So I'm using like out CmpLog, -m is none, so we don't want to use any memory limit for this. -c, which means that we are using CmpLog binary, and we need to give our CmpLog binary over here. That is imgRead_CmpLog, which we just compiled over here, as you can see over here. And then the normal command, that is /imgRead_afl++. Now let us go ahead and run this and see the difference. So you can see that within 10 seconds we started getting the crashes again. So if you recall, previously we ran the normal binary for like 7 minutes, we did not got any crash, and now here you can see that within like 10 seconds we had 5 crashes. Within like 30 seconds we have 6 crashes, 7 crashes. It is increasing. So this is how it works, and this is how you can use CmpLog feature. It is very helpful, and I will recommend, if you are fuzzing any binary which actually parsing some file which has some kind of headers, then you can actually use CmpLog feature. It is very helpful. It will help finding crashes easily. So this is how it works, and I'm going to cancel this now. And one more thing we can do is that we can try replicating one crash. Use the simple binary ++ out CmpLog crashes. You can see we have found like 8 crashes. So let us use and see. We found one stack buffer overflow in the printf statement. Let us replicate the second. What it is? It is a heap buffer overflow at memcopy over here. So let us also see another one. You can see that it is a large memory allocation failure. So CmpLog is very helpful over here, and you can use that. Now there is another approach you can take. If you don't want to use CmpLog, you can actually use a simple dictionary, and for that what you can do is that you can simply find all the string which are present inside your binary file. You can generate one dictionary, and you can use afl++-x option, and you can provide the dictionary file to that. It is recommended that you use both of this. You use dictionary as well as you use CmpLog feature, I hope that you have liked this video. If you have any questions, comments or feedback, then feel free to post inside the YouTube section. You can also reach me out on the Twitter. Feel free to subscribe, like and share my channel. That will motivate me to create more such videos. Till the next video, stay safe, enjoy your new year, and goodbye. Thank you.